Welcome back to Code and Current Studio. We are continuing to add to the Arduino Vehicle Cooling and Auto AC System project. In Stage 4, we're adding the final layer of realism to our HVAC simulation, visualizing fan speed and vent position on a dedicated LCD screen. This stage completes the automated climate control experience by showing users how the system responds to temperature differences in real time. We are reusing the components from Stage 1 and 2, the Arduino board, breadboard, temperature sensors, potentiometer, motors, the LCDs, the screens, and the servo motor. And we'll also be adding a few new components, another LCD screen, and servo motors for the blendDoor and the vent control. In this stage, we use the third LCD screen to display the current fan speed and vent mode. It's important to assign a unique I2C address to this screen distinct from the other addresses used in earlier stages, and ensure that the address matches the one defined in the code for proper communication. The LCD connects to Arduino via the SDA and SCL pins and requires 5 volts power and ground to operate. Two new servo actuators are introduced in this stage. The vent actuator, connected to digital pin 7, adjusts the airflow direction based on whether the system is heating, cooling, or maintaining temperature. It directs the air to dash vents, the floor vents, or bi-level, both the dash and the floor, depending on temperature logic. The blendDoor actuator connects to digital pin 6, adjusts with the temperature, and controls how much air passes through the heater core and the evaporator. This allows the system to deliver a range of temperatures. Both systems are connected to PWM-capable pins on the Arduino to allow precise control of positioning. Like the other components in this stage, the servos require power and ground connections to function properly. The LCD updates only when changes occur, reducing flickering and improving readability. All right, let's take a look at the code. The code begins by reading the cabin and desired temperatures, then calculates the difference between them to determine whether heating, cooling, or neutral airflow is needed. Based on the difference, the system adjusts the blower motor speed using PWM and sets the positions of the blendDoor and the vent actuators using Servo.h. The blendDoor actuator controls how much air passes through the heater core and the evaporator, allowing the system to deliver cold, cool, lukewarm, warm, or hot air depending on the temperature gap. The vent actuator determines where the air is directed, either through the dash vents, floor vents, or both. To enhance user feedback, the third LCD screen displays the current fan speed using the visual indicator like stars, and shows the vent mode as dash, bi-level, or floor. To avoid unnecessary refreshes and flickering, the LCD only updates when either the blower speed or vent position changes. This logic brings the system closer to real-world automotive HVAC behavior and helps learners understand how temperature-based decisions drive actuator control and user interface updates. All right, let's start the simulation. We can roll through each component again. So here's the AC compressor. This vibration motor represents the AC compressor. This would be the engine cooling fan. So we can bump the cooling temperature up a little bit here. This is going to be our blower motor. We can see we're at 2600 RPMs currently. This is going to be our blendDoor actuator. Adjust the flow, whether it's going through the heater core, the evaporator, or a little bit of both. And then here's our vent actuator. So if it's cool air, it's going to come out of the vents in the dash. If it's hot air, it's going to come out the vents in the floor. So right now we can see that we're bi-level. So it's splitting it, little out the vents in the dash, little out the vents in the floor. All right, the current temperature is 77 degrees. The desired temperature is 75 degrees. So 2 degrees cooler than what it actually is where it's at right now. So let's take it a lot cooler. (69 degrees), whereas the actual cabin temperature is 77 degrees. We can see that our fan speed is now at 2, so it's roughly 5,000 RPMs, still bi-level. All right, so now we went up, once it registered at 61 degrees, so now the air is coming out of the dash vents, and our fan speed is at 4, so that's at 10,000 RPMs. All right, so let's take it back to pretty close to what the cabin is. All right, we can see our fan speed is at 1, and the air is coming out both the dash vents and the floor vents. All right, so now, and we can see that our compressor's on over here as well. So let's take it up so it's fairly warm. So we desire it to be 83 degrees in the cab. This is our cutoff valve is also going to open to let the heat through the heater core, the coolant through the heater core. All right, we can see our compressor's off. Our fan speed is at 2. Our vents are at bi-level. So RPM is 5,000. So desired would be 84 degrees, current 77. So let's take it all the way up to 90 degrees and see if it changes. So we can see our fan speed is now at 3, and the heat would be coming out of the floor vents. Try adjusting the potentiometer to simulate different desired temperatures. Watch how the fan speed and the vent mode respond on the LCD. Can you add manual override buttons? If you're following along, consider picking up an Arduino starter kit. It includes all the components used in this project and more to expand your learning. Check the video description for links. That's it for stage 4. You've now completed the automated climate control simulation. Don't forget to like, comment, and subscribe for more Arduino tutorials.